Good morning, everyone. We are heading to our second plenary session on Keynote paper, how do you like to name it, by Maciej Janicki, who is sitting in the second row here. You think already know him. We have been working together with Maciej with the Filtech project almost already 2 years, not 2 years, 1.5 years, and that is the first event we actually meet in person. He has been really the hero in our Filtech project because as a computer scientist, we haven't had before the luxury to have a computer scientist in our team, so there have been really major developments in the study of Finnic songs with the help of Maciej and Edu also. Yes, Maciej has been working with the environment for studying songs, for comparing, for exploring songs, and there is more possibilities to do it than we ever have dreamt. And if we have some research questions, he comes up with more answers than we can proceed, usually very quickly. So we know what we are going to hear now. I guess I already know much of it, but certainly not all. So please, Maciej, text similarity and alignment in the study of Finnic oral poetry.
Thank you, Mari, for the introduction and for inviting me here. So, unlike most people here, I don't know much about poetry and literature, so it's been fun and very interesting for me to be in this conference. I'm just a computer scientist who happens to work with poetry in the recent project, and today I'm going to present you some experiences from this point of view. So we've heard already a little bit about our project with the acronym FILTER, which stands for Formulaic Intertextuality, Thematic Networks and Poetic Variation Across Regional Cultures of Finnic Oral Poetry. And it is a cooperation of 3 institutions. So we have the Finnish Literature Society with Kati and Jukka, both here, the Estonian Literary Museum with Mari and Liina, also both here. And as the third partner, we have the Human Sciences Computing Interaction Research Group, which is at the University of Helsinki, Department of Digital Humanities, and is represented by me and by Eetu Mäkelä, who is my boss. So we are the computer scientists in this project, researching how computer science can help in such humanities research questions. Sorry. Okay, so the corpus that we are working with is consists of a couple of collections thrown together that are already big collections. So we are working with the Finnish collection of runo songs called Suomen kansan vanhat runot, or SKVR, which translates to Old Poems of the Finnish People, and is a very large collection of around 90,000 poems collected from oral poetry that was published also in print throughout the 20th century. And then we have the Estonian database of Runo songs, which is of similar size, also around 100,000 songs. And both of those are quite well known and have been available publicly for some time. Then the third corpus that we have hasn't been available before. This is the corpus of previously unpublished poems that were in possession of the Finnish Literature Society, that has right now been digitized and is for the first time available for research together with these previous ones, thanks to Jukka mostly and his work. And this one is also quite large, so here we have again around 80,000 texts. And as an addition to that, we also have some printed works that have some relationship to Finnic folk poetry, which is Kalevala, the Finnish national epic, Kanteletar, which is a collection of folk poems edited by the same collector as Kalevala, which I'm going to say a bit more about later in this presentation. And then Kalevipoeg, the Estonian national epic that you've heard about yesterday. So all these texts have certain common characteristics. They are written in a meter called Finnic tetrameter, which in its basic form consists of 8 syllables. And you can see some examples of what such texts look like on the right. The first example comes from SKVR, so the collection published in Finland, but the language is not actually Finnish, it's Karelian, so more to the east. And it is a fragment of an epic story, which also appears in Kalevala, but here more the oral version. And then the other text is from the Estonian database, and it's in Estonian. So just to give you a small sample, this is what the texts look like. And most of them were collected in the 19th and early 20th century. The entire range is a bit larger, so the earliest texts in SKVR are, I think there is even something from the 16th century, but very little. And most of it is the 19th and early 20th century, where people became interested in this oral tradition. And to give you some numbers, so we throw a couple of large collections together that, to my knowledge, haven't been studied together as one corpus before. And this altogether gives us a corpus of 275,000 something poems, or what a computational linguist would call documents, so units of text. And they consist altogether of 4.3 million verses or lines. When I say verse, I mean the same as line. And of that, we have 3.4 million unique verses. So most verses don't repeat entirely in the corpus, entirely in the same form. And just to have a small impression of this, I said that SKVR, so the collection published in Finland, was also published in print. And this is what it looks like, although this is not the entire SKVR, it's just roughly half of it, so up to volume 7 out of 14. And some volumes consist of multiple parts. So it's half of SKVR, so around 1/6 or 15% of our corpus. So our entire corpus on paper could be imagined as something more like this, which is simply this image copied 6 times. So in other words, it's a lot of text. And because it's collected from oral tradition, we have a lot of relationships between these texts, ranging from exact duplicates, because a text might have been published multiple times for some reason, or fragments of one manuscript might have been republished at some other place for various reasons. Then we have things like, for example, 2 different performances of the same poem, even by the same singer, but at different points of time to different collectors, which is not entirely the same text anymore, typically. Then we have, for example, texts that were known by family members and then collected from father and then son 50 years later, for example, which bear even more differences. And then we have texts that spread regionally and that spread more broadly. So, in other words, we have a lot of relationships and overlaps between these texts that are not that obvious to recognize. And because of the size of the collection, it might be a good idea to think of some computational methods to recognize these relationships, because there is just so much of it. So here's a small example of how similar texts can look like. We have two versions of a snippet of a poem called The Song of Lemminkainen, which is again an epic story about a hero. And as far as I remember, the version on the right was performed by the son of the singer who performed the version on the left. And the time difference is also a couple of decades, something like 30 or 40 or maybe 50 years. And when we read it, it looks like the same text. Like we can recognize the same lines in roughly the same order, although there are some differences. For example, this line, "Yht ei kutsu lemmingeistä," it's not here, but we find it a couple of lines higher up here. But most of the lines are going to be in the same order, because of course it has to tell the same story. But then we see that also the lines that contain the same text are not exactly the same when we compare the sequences of characters. So we have, for example, the line "Sogiat venosin soldi" on the left, and "Sogeat venosin solti" on the right, which reads more or less the same, but if we look at it carefully, every word is different. So if we want to design a machine method to compare such texts, we need to take it into account. We can, for example, look at just entire words that are the same. We need to recognize similarity even below the level of word. So this already gives us a glimpse of what we're going to need to do. And when we now see how much similarity there is in the corpus, four computational tasks arise that I thought would be interesting to solve. First, if we already know that some two texts are related and it would be interesting to compare them, we would like to produce such an alignment automatically. So just automatically recognize which lines are the same, which are different, and then highlight what is different, what is the same, exactly like we have in this picture. So this alignment also has been produced automatically. But then also, we would like to summarize this alignment in some numbers that tell us how similar these texts are. So we would like to count, for example, how many lines are aligned, how many are not aligned, and produce some number that tells us the similarity of these two texts, so that we can then compare it across the different alignments, which texts are more similar, which are less. And as a third task, of course, we don't know in advance which texts are interesting to read together, so we would like to find that automatically as well. So we would like to automatically find pairs of similar texts in the corpus that are worth aligning and that produce alignments with good similarity. And then finally, when we do that, we can look at the whole table of pairs of aligned texts, and we would like to get some large-scale overviews of the identified similarities. And from that, maybe we can say something about the oral tradition, or how the Finnic oral tradition works, how much similarity we find there. And these are the questions that I will address in this talk. And I will address them with two very simple computational methods that are actually so simple that we can do the calculations even by pen and paper, and we will go exactly through how they work. And when I first tried these methods, I tried them as sort of the first attempt. I thought this will be the baseline, and then we can look for something more sophisticated, but quite surprisingly, it turns out that this just does the job, and there is no reason to look for anything more sophisticated. So instead, we can concentrate more on what we do with it now that it works. So we will go through these two simple methods. The first is for comparing individual verses. So we take two verses, two lines, and we would like to have a number that summarizes how similar these verses are. And then the other one will be for comparing entire poems. For comparing two lines, I've already said that we need to go below the level of word, because there can be words that are spelled a bit differently. There are different dialects in the corpus and even different languages, but so we will have partial similarities between words. And a good representation for that turned out to be to look at character bigrams, so pairs of adjacent letters. And we can represent each verse as a vector of bigram frequencies. So for example, for each pair of adjacent letters that is possible, we have such a dimension, and into it we put the frequency of this bigram in this particular verse. So for example, we have the verse E palleula vaina merista, and it contains the bigram A once, and the bigram IP once, and the bigram IB 0 times, and so on. And then we have another verse, Eiba leuva vaina merista, which sounds similar. And if we look at the bigram vectors, they are also similar, although not entirely identical. So the idea is that our vector representation captures this kind of similarities, while it is tolerant to small differences, and also it is tolerant to such differences like, for example, changed word order, because that might also happen. And here we don't store any information about the ordering, we just throw the bigrams into so-called bag of bigrams. So the information about how they are arranged to words is lost, and this is good because transposed word order happens, and this will still result in similar vectors. Now, we don't need to have a dimension for all bigrams, because some of them are very infrequent, so if we restrict it to, say, 300 most frequent ones in the whole corpus, we don't lose much information, because those rare ones mostly don't occur, and we don't need a long tail of zeros here for most vectors. It wouldn't change anything. So we can restrict it to, say, 300, and that's enough. Now, how do we compare these vectors? So if we have such a representation, how do we find out how similar two lines are? We do it with a very standard metric called cosine similarity, which is very easy to calculate. The idea is that we multiply corresponding coordinates. So we take something like 1 times 1, 1 times 0, 0 times 1, 1 times 0, and so on. And that's what this formula also says. And then we add it all up. So we take 1 times 1 plus 1 times 0 plus 0 times 1 plus 1 times 0, and so on. This we take in the numerator. In the denominator, we take the squares of coordinates for each vector, so 1 square plus 1 square plus 0 square plus 1 square, and so on. The square root of all this times the same for the other vector, 1 square plus 0 square plus 1 square, and so on. This is the length of the vector. So geometrically, if these were coordinates in some space, then this formula would give us the length of the vector, and the whole formula would give us the cosine of the angle between the vectors. So the cosine is 1 if the vectors point exactly in the same direction, so if they lie on each other, so to say, while it is 0 if they are orthogonal, so if they point in exactly other directions and have nothing in common. So this is the geometric interpretation. But the main point is that this gives us a number between 0 and 1 that tells us how similar these vectors are. And this is all we need. So now if we have a certain verse, like for example, E palleula vaina merista, we can look for similar verses across the whole data set, and with some indexing, we can search the dataset for most similar vectors, and we will get answers like this here, E palleula vaina merista, which is, for example, has similarity 0.86, and we can see that it consists of roughly the same words. We can probably recognize it even not knowing the language, that these are the same words, but they are written slightly differently or have slightly different forms or come from a different dialect, maybe something like this. And then when we look further down the list, we can find a couple of variants from that. But then suddenly we find eipä sopi Väinämöistä, and here we can see that this word is already different, and this is indeed different verb. The first one, eipä löyä Väinämöistä, means doesn't find Väinämöinen, and Väinämöinen is the name of a hero, and this here means doesn't hit Väinämöinen. So it might be considered a synonym in some contexts, maybe, but we're not even sure of that. Anyway, it's another verb. And now, maybe we would like to distinguish these two cases a little bit, because the first one really says the same, it's just written a bit differently. The second one is related or somewhat similar, but it says something else. So what we did in our research is we introduced the definition of an equivalent verse. And an equivalent verse is one that says, or a pair of equivalent verses says the same with the same words, and the differences can be just dialectal, morphological, orthographical, but generally it uses the same words. So the verses up to here would be equivalent, but these two would be equivalent with each other, but not with the ones above anymore. And now, how do we distinguish that? It turns out that just figuring out which value of similarity to make the cut at is not necessarily a good idea, because it will vary from case to case. But what we can do instead is we can look at the structure of these similarities and see that, for example, this verse has a couple of equivalent verses that are all similar to each other, while the similarities to these two will be more loose, and they then will be similar to each other again, but not anymore to those with löyty. So this task can be solved by a so-called clustering algorithm, where we see the verses as nodes in the network, and the edges between them are the similarities, and the thickness of the edge or the weight of the edge corresponds to the cosine similarity between the two verses. And now we see that there seem to be two groups in this graph, which are both more thickly connected with each other than between each other. And a clustering algorithm is able to identify this and divide this graph into these two groups. And the algorithm that we use for that is called Chinese whispers, and it works well with even millions of such verses, and a graph consisting of millions of such verses. So of that we build a small user interface that I will say more about in a moment, but the idea is that now if we read a text and we find this verse in a text, we have a little bar here that shows how often this verse occurs across the whole data set. And this wouldn't have made sense without this clustering and similarity method, because as I said at the beginning, most verses are unique, so they don't occur multiple times in the corpus in exactly the same form. But if we divide them into those clusters of equivalent verses, we can measure the frequency more realistically and disregard some of these differences. So here, for example, for this verse, we find 5 similar occurrences in the whole corpus, and if we click at it, we can go to a page where we have a list of all these occurrences together with links to the texts where they occur. And this is something we described in a paper that is almost published. It will be published hopefully in a couple of days or weeks in Digital Scholarship in the Humanities. And it's called Exploring Finnic Written Oral Folk Poetry Through String Similarity. So that's what I wanted to say about similarity of individual lines. This clustering is a bit of a side note. The main idea here was to have a number between 0 and 1 that summarizes the similarity between the lines. Now let's go to the other method, which is similarity between entire poems. And how do we produce these alignments, and how do we calculate from them the similarity between entire poems? And for that we will use a method that is very well known and very old. It's called edit distance. The basic method is, I think, something like 70 years old, so almost as old as computer science itself. And it's very, very widespread and well known. So first I will present to you the basic algorithm for edit distance, and then I will show how do we modify it to operate on whole poems. But to simplify it, let's take a first example where we do it on individual words, and as words, let's take the title of this conference, so plotting and poetry. And the task is to turn one word into the other. So how do we turn plotting into poetry? Using the so-called edit operations. And an edit operation is either an insertion or a deletion or a substitution of a single letter. And the question is, how many operations do we need at minimum to turn one word into the other? And in this case, the answer is 5. And here is one such transformation, not the only one, but one with edit distance 5. So we see that we need to remove the L, then replace the T with the E, replace the I with the R, N with Y, and remove the G. These are altogether 5 changes with which we turn plotting into poetry. And how do we find this out? How many changes we need and which ones? For that we have a well-known algorithm. It works by filling in a table. So we draw a table in which the letters of one word will be the rows and the letters of the second word will be the columns. And in each place in the table we will enter the partial edit distance between the prefixes of these words. So for example, in this place, which corresponds to plo on the left and po above, we will have the edit distance between plo and po. And then going further, here we'll have the edit distance between plot and po. And here we will have the edit distance between plot and poe. And we will find that these distances depend on each other. So we can calculate each further cell very easily based on the neighboring cells. So let's start with the trivial case. How do we fill in the first row and the first column? So the first row, here we don't have anything. So it's the empty string, and we calculate how many changes we need to turn the empty string to an empty string. 0, of course. How many changes we need to turn an empty string into P? 1 insertion. Into PO? 2 insertions, and so on. We can only do insertions because we have nothing to change. So it will be just the number of letters we have above. And the same here, it will be just the number of letters on the left because we can only delete these letters, we have nothing to change. And now, the rest of the table we fill in using the formula on the right, which tells us that each cell will be filled in based on the one immediately on the left, one immediately above, and one above and on the left. So for example, how do we enter a 0 here as a distance between P and P? We just need to consider what is the last operation that we need to do. And if the last operation that we need to do is an insertion, this means that we're coming from the left. So we already had a P here, and we are inserting now a P to get here. So by inserting one letter, we can move one step right. And likewise, by deleting one letter, we can move one step down. So if the last operation was a deletion, this would mean that we would be coming from here, and we would already have a P here and delete it. And then, if the last operation is substitution, this means that we come from the top left, because we move one letter in one string and one letter in the other string. And now we need to consider what are the costs of these operations. So an insertion and a deletion is always a change, so it always counts as 1. That's why we take the value from the immediate left plus 1. And for the other one, we take the value from the top plus 1. And then a substitution is not always a change. It depends whether the letters that we take are equal or not. If they are the same letter, then we are not changing anything, so we don't need to count it as a change. And if they are different, then we do. So what we're adding here is such a delta between the last letter of one string and the last letter of the other string, and this is 0 if they are equal, because there is no change, or 1 if they are not equal. So now we consider these 3 cases, and because we are looking for the minimum edit distance, we need to see which of the numbers is smaller. So here we will have 3 candidates for the 0. It's either the one from the left plus 1, or the one from above plus 1, or the 0 from above left plus the difference between the two letters. And because they are both P, the difference is 0. So this case will be 0 plus 0, and it's the best one here. It's the lowest number. That's why we enter 0 into this place. And we do the same with the remainder of this row. So for example, here we would consider 2 plus 1, 0 plus 1, and 1 plus 1, because now O and P is different. So the winner would be 0 plus 1, which is 1. And based on this principle, we can fill in the entire row, and then we would proceed the same way here. So it's really something that we can do on paper, and it's a very good exercise to understand how the algorithm works. Once we fill in the whole table, we will have a good understanding of how it works. And now the value that we get at the bottom right is the edit distance between the entire strings, so between plotting and poetry. And so we have the number of operations here, but we don't see what is the alignment or what are the changes that we need to make. But we can get this very easily from this method as well. We just need to remember where we are taking the optimal value from. So for example, here we have the 3 candidates, left, top, and top left. And we took the value from the top left, so we would need another table in which we enter this information. For example, as an arrow pointing to the top left. And we can have another table with arrows that always tells us from which cell we took the optimal value. And now we can get the alignment by simply starting at the bottom right and following the arrows. Following the arrows, that will give us a path that leads all the way to the top left. And this will mean that, for example, the last arrow points up, so it means that the last operation was a deletion. So we have the deletion of this G, and then we move one step up. Then this arrow points to top left, which means that it was a substitution. So we take one letter from this string and one letter from this. And this is the way we read it. So top left is substitution, up is deletion, and left, which we don't have here, would be the insertion. Okay, so this is how we, in general, calculate edit distance. Now I'm going to modify this a little bit so that we can accumulate some similarities. And okay, I'll show the previous slide once again. You can see that we are making some strange substitutions here because we only consider whether the letters are same or different, but if they are different, then every difference counts the same. And if we looked at it from the phonetic perspective, for example, it would be a bit strange to substitute a T with an E or an I with an R. And we might think of a modification of this distance that is more phonetically motivated, so some letters can be similar to each other and more likely to be substituted. So this is the idea of a weighted edit distance, and now we also flip it a little bit so that insertions and deletions have weight 0, and delta between two letters is the similarity and not the difference. So 1 is now the maximum similarity, which is identical, and 0 is that they are completely different. So it will work basically the same, but now instead of minimum, we're looking for a maximum, and the things that we are counting are not the costs or not the changes, but rather the similarities, and we want an alignment that captures maximum amount of similarities. So, for example, we can define our distance function in such a way that it's 1 if two letters are identical, and then we have such cases like I and Y, which would count as 0.8, so they are almost the same, they can describe the same vowel, and R and L is also kind of the same. T and R, T and L, and E and I are still somewhat similar, so we would count it as 0.5, and then 0 otherwise. And with that, if we now look for the maximum weight alignment, we get a one like this, that is not the minimum number of changes, because it has 6, and we have already seen that 5 are possible. But these changes are better motivated phonetically, because, for example, we substitute T with an R, we substitute E with Y, plotting, poetry, so it's almost the same. And according to this weighting function, this one is optimal, and it has a total weight of 4.3, so this is the sum of all these similarities here. And Now we already have a way to align things. We will in a moment see how it works with entire poems. But my second goal was to derive some numbers from this alignment that tell us how similar the two sequences are. And one of these numbers we already have is just the total weight, so the sum of all the similarities between the letters. But it's not very practical because it depends on the length of the words. So if we take longer words, we might have more similar letters there, so it's good to normalize it by the length of, for example, the first word or the second word, and both will give us a number between 0 and 1. So here we have the left normalized similarity, which is just divided by the length of the first word, right normalized, which is just divided by the length of the second word. And to make it symmetric, so to make it so that the distance between plotting and poetry is the same as the distance between poetry and plotting, we can take a harmonic average of these two, which is defined by this formula. And this will be the number of letters inside substitutions here divided by the total number of letters that we see in both words, where the black letters are counted as 1 and the blue letters are counted as much as similarity they have. So these ones as 0.8, these ones as 0.5. So this is an interpretation for that. And this gives us a symmetric number that tells us how similar these strings are, and that is between 0 and 1. So we can express it conveniently as, for example, 61%. Now, I have presented it on words, but words are sequences of letters, and likewise, poems are sequences of lines. And we have already seen that we have a method to compare lines so that we get a similarity between 0 and 1. So we can just put it into this algorithm now, and we can start with 2 snippets of poems that were, again, the Song of Lemminkainen that I've shown before. And some lines have a similarity. We can cut it off at some point. Here I don't take similarities between 0.5 because there would be too much noise. And we are left with something like this. And now if we apply the same algorithm, fill in this table, we will get some similarity between those sequences. And also, again, if we make another table with arrows that tell us where we took the optimal value from, we will have the alignment that I have shown previously, which tells us which lines should be presented next to each other. So I need to speed up a little bit, but you've already seen this idea. And then I can compute these measures that tell us finally that these poems are 58% similar, for example, and also 54% of the left one is contained in the right one, and 62% of the right one is contained on the left one, something like this. So now the idea is to compute exactly this on all pairs among 275,000 poems, which is easy to say, but we needed to do some tricks in order to be able to compute this, because it's just very many pairs. So I won't go into detail about how we optimized it. We can talk about it later if someone is interested, but the basic idea is to use vector and matrix operations and to compute many things at the same time, and then to run it on a graphics processing unit that makes such computations faster than a CPU, than a normal processor. And in our project we have access to a supercomputer, exactly the one showed in the picture, which was able to do it within 64 hours. But it's not something that a normal computer couldn't do. A normal computer would need just a bit more time, maybe a week, maybe 10 days, but it would be also possible. And as a result, we now get 16 million pairs of similar poems that were aligned this way and that fulfilled some criteria so that we could say they are similar enough to be interesting. And the criteria are that the row similarity is larger than 2, so they have at least 2 lines in common that are exactly the same, or a bit more lines in common that are not exactly the same, that wouldn't count as entire one. And then at least 10% of one poem is contained in the other, so either the left or the right similarity is at least 0.1. So such pairs we keep, and then we get 16 million of them. And We have built a user interface out of it that allows us to browse these similarities locally. So we can read poems there, we can look at verse clusters as I've already shown, but we can also look at similar poems. So for each poem, or almost each poem, we get a list of similar poems that were computed automatically and that tell the reader, you might want to look at this as well. And maybe I can quickly show what it looks like. Can we switch to the browser? We can't. Okay. I will need it later as well, so it would be good if we could. Okay, so I will just continue. And maybe we can share the slides later so we can click at those links and see our interface because it is publicly available. But I will need to finish soon, but I would just like to present what we can do now that we have the results of these computations. And the idea was to make a quantitative analysis where, based on this data from the whole corpus, we can say something about the oral tradition. And here are just 3 research questions that I came up with, but probably more can be done. So we can generally look at how this similarity is distributed and how it relates to the information that we have about the texts, in other words, the metadata. So, for example, are similar poems sung by the same singer, or they're sung by family members, or they're sung by people from the same parish, same region, and so on and so on. We can compare their distances in time and their geographical distances, and maybe on this basis say something about how these similarities spread. The other thing that we can restrict is to compare the oral tradition with the printed works and see how the printed works were based on the oral tradition, and also how the printed works fed back into the oral tradition. And finally, both the Finnish and the Estonian database have a type index that was constructed manually that annotates poems with, so to say, titles or motifs that they contain. And maybe the similarity computation can help improve and evaluate these type indices. So as to the first thing, here we can see the overall distribution of this similarity on those 16 million pairs that we have. On the left is just a histogram, so we see the different ranges of similarity and how many poems we have for each, and we can see a peak around 0.2. But the more valuable information is that for each range of similarity we find quite many pairs. So if we're interested, for example, in almost exactly the same texts, we also find a lot of them, and also ones that are not entirely duplicates but almost the same. And on the right we have a plot that shows the rank versus score. So if we order the pairs by similarity, from this we can easily read that, for example, we have around 5 million pairs with score above 0.4. So we take the 0.4 here and we get 5 million on the x-axis, and around 10 million that have score above 0.2 and so on. Then we have some things that I need to skip, unfortunately, but this one might be interesting because this shows us how this relates to the metadata about the poems. So now we can round the similarities to 0.2, 0.3, 0.4, and so on. And for each of these groups, see how many poems there are annotated with the same types, which should mean that they have the same content, and this is the green curve on both plots, so for the Finnish and for the Estonian dataset. And the curve goes up, which is to be expected, but what is maybe not so expected is that it doesn't go up all the way to 1. So even for identical texts, they are not always annotated with the same titles. And this is particularly visible for the Estonian database. This is because the type index is not quite finished, and there are many poems that are still not annotated with these titles, and that we can now recognize in this way, that maybe they will be similar to something that is annotated, and then we can transfer these annotations. Then we have curves for same county, same parish, same collector, and for the SKVR also same volume, and because volumes are arranged by counties, this is almost the same as same county. And also, unsurprisingly, these curves all go up, so the more similarity poems are, the more likely they are to be from the same parish, same region, same collector, and so on. But also it's worth noting that the curves are far from one, so we still find very similar texts that are far away geographically or in time, and so on. Okay, here are also year differences and geographical differences, so we can plot this for all the pairs. And also the most interesting information there is how long the spread is. So we find similar pairs that are as far apart as 300 years or as far apart as 1,000 kilometers. And then we can, with outlier analysis, we can take the most extreme ones according to different criteria and look at them. And here I have again some clickable examples, but we probably wouldn't have time to look at them. But if we show the slides, you can click them and show similar texts. The most, so to say, stable types of poems, so the ones that tend to stay the same across large amounts of time or across large distances, tend to be, for example, charms that have a very fixed form, and it has to be in the same text because otherwise it wouldn't work probably. There are also proverbs that are very short texts, lullabies, children's songs, so these are the types of fixed texts. Now, I wanted to say very briefly about how we can study the similarities or relationships between the oral tradition and literary work, because we also have literary works in the corpus. One example is Kanteletar, which is a large collection of folk poems compiled by Elias Lönnrot, the same one that also wrote the Finnish national epic Kalevala. But Kanteletar is closer to oral tradition, so it contains individual songs that are very close to the songs that Lönnrot indeed collected. It contains 676 poems in total, was published in 1840, and is very well known and influential. And what we can do with our data is we can restrict the analysis to pairs where one poem comes from Kanteletar and the other one does not, and see what are the relationships there. And we can study things like, for example, what is the difference in time between them, and divide them to pairs where the other poem is from before the publication of Kanteletar or after. And when we study the poems that were published before Kanteletar or collected, these might be the ones that Kanteletar is based on, for example. So it might be interesting to see the sources for this work. And then the ones that were collected after it might be influenced by it. So it might be that people read Kanteletar and then introduced it back to the oral tradition. But this is difficult to distinguish from the oral tradition that exists independently of Kanteletar and where people just learned it from the oral tradition continually. But we can study these pairs, we can make, again, different plots there. We can also plot it on a map, these two data sets, so before the publication of Kanteletar and after, and see, for example, on poems from what regions is the Kanteletar based, and we see that it's mainly here North Karelia, White Sea Karelia, and then on the other map we have similar poems to Kanteletar throughout the time after its publication. And these maps can be interesting to study, but they can be also very misleading. So I just show this also as an example of we should be careful with simple interpretations. For example, what we can see here is that on this map, Ingra is displayed very prominently. So this region here is very dark, which means that there are a lot of poems here similar to Kanteletar, while here there aren't any. And the interpretation that we are tempted to think of based on just these maps is that maybe the poems in Ingra were influenced by this literary work. Maybe that's where it spread and then was collected again. But there is another explanation for that that is much simpler, which is simply that the data that we have from Ingra was all collected, or almost all collected, after 1840. So it might as well be independent oral tradition, it just wasn't observed before. So we need to be careful when interpreting this. We need to look at many different visualizations and always be careful with simple explanations. We can also arrange such pairs by collector and, for example, see what are the collectors of the most similar poems before Canteretal was published, and because it was published by Elias Rönnroth, this is no surprise that we find most collections of him that are similar to this work, but also of other collectors that we might want to study, and here we could click at the individual examples and see the texts. And the same after, we can also arrange it by singer and see which singers were influential there, or which singers were possibly influenced by this or continued the same tradition independently. And then the last thing I wanted to talk about was enhancing the type indices, which is maybe the most practical application of this. So as I said, we have titles of poems, but in both big databases, not all poems have these annotations at all. So for the ones that don't have them at all, we can look for a similar poem that has it, and maybe we can annotate it with the same title, and this way we have found some of the well-known poems that weren't annotated in SKVR, in the Finnish collection. In total is 711 of them. In the Estonian collection we found 30,000 of them. This is because, as I said, the Estonian type index is work in progress, and I really hope that we can apply this approach to facilitate this work, that now someone would simply need to look at these similar texts and click OK if the title can be transferred, which is much easier than looking at a text in isolation. Then we can also study what are the, so to say, irregularities in the type index, so we can have a look at almost identical texts that are nevertheless annotated with different titles. And this can have many reasons, and I'm not saying whether it's right or wrong, but it's just good to know that such cases happen and to be aware of why it happens, because we might expect that if the text is the same, it should be annotated with the same titles. And there might be different reasons why it's not the case. Some titles might be, for example, duplicates of each other, so the same type of poem was entered with two different titles. Some might be that they contain both motives, for example. For example, here, the Lord will wake you up, and sleep, sleep, my grass bird, both refer to a single line, and these lines often occur together in one short song. So they are related types, and maybe the poems that contain both of them should be annotated with both, or something like this. This is the kind of questions that we can see emerging from this analysis, and we can think about what to do with it. And then I also mentioned that we had a corpus of unpublished poems which are not annotated at all with this type of annotations, and because they are written in the same language as SKVR, we also are able to transfer annotations for 40,000 poems right from SKVR by just using these similarities. And then the last thing, we were interested, because the Finnish and the Estonian collection haven't been studied together before, we were interested whether there are some common motives to Finland and Estonia, or to the North Finnic and South Finnic region more generally. And it turns out there are not that many, but there are some. And for example, there is a well-known song, The Maid to be Ransomed, which is a very fixed form and is known both in Finland and Estonia. And it turns out that our method for comparing these similarities is so flexible that it can even recognize similarity between a Finnish and an Estonian text. So it's a pity that I can't show you an example here, but we could see the Finnish and Estonian text next to each other, and there is a lot of similarity. There is enough similarity in terms of these bigrams that we can recognize it. So there are similarities between entire texts, like for example this song. There are also smaller similarities when only a couple of lines is similar, so 2 or 3 lines, like for example, Singer's Reward, which is 2 or 3 lines about I won't sing about money without money because singing costs money, or something like this, which is put into different contexts, and the context around it is not similar between Finland and Estonia, but these 3 lines are known in both. or some other motifs here where there are also such partial similarities. And here on the map you can see all the Finnish poems or Indian poems that have a counterpart in Estonia, or Estonian poems that have a counterpart in Finland. And this shows you again the range of this spread. Okay, I needed to speed up a bit, but I'm more or less done. So I wanted to show you the possibilities that this similarity computation gives us. We can now have the relational view on collections where we look not at individual texts, but at relationships between two texts. For example, this generates new data, like their distances in different ways. The justifications for large-scale patterns are often non-trivial, as I've shown with the maps. We need to be careful with interpretations and always look at the individual texts to see what we're counting. And yeah, as a last thing, is it possible to generalize to different collections? And maybe it is, because the methods are not really dependent on the language. But I think it's not guaranteed that in other collections we will find as many results, because this oral poetry really contains a lot of such similarities, so there is a lot to find there with this method. But maybe it could be tried for other collections as well. Sorry for speeding up a little bit, and thank you for your attention.
Wonderful. Thank you for your presentation and all this work, what you have done for with the Renaissance questions. Yes.
Thank you very much, very impressive. I have two, I hope, good questions. So the first one would be about the line similarity calculation, right? So you use the cosine distance on the big graphs, but I wonder, because you are still calculating this on the verses, right, on the single verses, and it looked like very binary at some point, right? Because you have a lot of like ones and a lot of zeros as well. So why not to use any binary distance, and have you tried it, and why the cosine in this case? Because there would be like also a natural difference between longer lines and shorter lines. Like longer lines will allow more like inflation of some frequencies.
Yeah, so you mean what's the difference if we enter the count of the bigram or just one if it occurs, right?
Right, yeah. Why just can we use Jakar or whatever?
Yeah, we could try this. One reason why we use the cosine is because it's easier to compute on a very large number of verses.
That's true.
So
yeah.
it's just a matrix multiplication. But we can use different weightings there. So we can, for example, turn all numbers that are non-zero to just ones.
Mm-hmm.
And the difference is indeed relevant for example, onomatopoeic verses or heavy alliteration, where there is a lot of the same big bigram. It's sometimes a bit overweighted with this basic thing. So for example, we can have verses like oi 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 something, and then oi oi ois are similar. This is a problem, and then it might be a good idea to downweight it this way.
Thank you. And the second question, if I may, is about the distribution of the similarities, right? Do you showed this curve that is left skewed. Do you expect that we can similarly to how people do it with languages and dialects to infer some bimodality in the distance distribution to find kind of the differences between like non-similar texts, right? The texts that are texts that are derivatives from some kind of product text. Sorry, there is no such thing, but like let's imagine some type, right? The type of text, and the texts that are completely different. Do you see this in your data?
Well, actually no. So I've shown the histogram, and it wasn't bimodal. It just went smoothly down, and I think this is also interesting because
sorry, it wasn't very smoothly going down. There was some. I mean, we can never infer like the processes that generated the distribution just from looking at the distribution, right? There could be still a bimodality, and there was small like peak somewhere in the middle. If you can, yeah, if you'll show it back on slides.
Can we show
so
the
it's
slides?
like interesting to think about this.
Yeah, so that's what the histogram looks like, and if we had such a hypothesis that some texts are the same text and others are not, then maybe we would see a peak somewhere here, and then it would go down in the middle. But what we see instead is that we have the texts that are exactly the same, and then we have the texts that are almost the same, and almost the same, and almost, and it transitions very fluently to texts that are loosely related, so we really find everything in between. And
I would still not throw this hypothesis up, because there is a bump around 0.5, 0.6 that might actually tell you that these are two different processes that do generate. I mean, the global processes that can generate this distribution, and I would maybe try to look into that. Yeah. Maybe,
yeah. Do you have some idea how we could test this hypothesis?
I know that some of the work that linguists do, they use some inference methods to kind of try to infer bimodality in histogram, and so we might, you might look at that and kind of decompose this histogram into two, and then look for the same text similarities, maybe use metadata, right? So for this second distribution that is on the right, you can use the metadata to infer maybe they are the same type, or they're the same type registered texts in the indices or something like that.
That might be interesting to try.
Yeah, but very cool. Thank you.
Yes, Levente.
Thank you. Yes, for me also it was amazing. So we were trying on a roughly similar corpus to do something that looks for parallelisms and repetitions, but we certainly not achieve this kind of results. So it's really amazing. Just one question: are you examining also the grammatical similarity, the syntactical similarity? Is it possible, or as you were using only the bigrams, it's just only based on the lexical repetition? Because for other reasons, for the composition, it might be also interesting to know how strongly the grammatical structures are similar in the same points or in the same folk traditions.
Yeah, so the problem there is that the language is there is so much variation in the language, it is so non-standard, and the spelling widely differs, so anything that goes more into depth linguistically would be very much effort to just reliably annotate. So that's why we do it so shallowly.
Thank you.
Any other questions? Anne-Sophie? Yeah.
Yes, thank you so much. That was very interesting. I had a question. You showed how when the Karatelan, when those Finnish texts were collected, not the Kalevala but the other corpus, that after it was collected, then you have and it might be a spread of that, or it might also be that more data is being collected. So the first interpretation that we haven't in the diagram is not necessarily true. But my question was, so after that event of the Canterata being published and collected, do you see, when you compare the data from before to the data from after, a higher inter-regional similarity, as if there had been a process of standardization or the disappearance of a variety, a greater variety that could have been there before?
Yeah, that's one thing that we would like to study. We haven't done it yet, and I think it can be shown with very simple aggregate views or plots. We really need to look at the texts to be more sure of what we're saying. So this is more interpretive work for scholars in literature that can maybe be started by using such tools.
Thank you.
So many ideas, and we have a question online. Elena?
Thank you so much for your very inspiring lecture. I have a couple of questions. First, have you been using phylogenetic software? And second, have you been using some coefficients or some other ways to account for something that you would count some as crucial difference rather than just usual difference? I hope it was kind of clear enough.
I didn't hear the first one, so what kind of software?
Phylogenetic software.
Phylogenetic, okay. Well, not really. We have done something roughly similar, which is that if we have pairwise similarities between poems, we can make hierarchical clustering and plot a dendrogram out of it. But it wouldn't be possible to tell like which poems come from the same source or something like this, because the data is too biased for this. It's so random sometimes what was collected and what really existed. So we should be careful with such interpretations. But we can plot a dendrogram just to see how the poems group together, for example. And we have such functionality in our interface. And the second question, have we used any coefficients to somehow weight the differences, the different types of differences? We haven't, so I haven't recognized anything by looking at these comparisons that would be particularly worth weighting differently or emphasizing in the algorithm. There is just too much different things, and it's kind of a mess.
Thank you.
Thank you. You? If there are no questions, I have a present for you, but it is upstairs.
Okay, thank you.
I will bring it to you, and we'll have now coffee break behind the curtains. Thank you once again.
Thank you.